Welcome to Unit 2, Lesson 3. We're looking today at the structure of ionic and metallic solids. So we're going to first look at ionic solids and kind of see what their properties are, and then we'll get into metallic solids and then also metal alloys. So just to kind of review, the difference between a covalent and an ionic compound is first of all, covalent compounds tend to be two or more nonmetals forming compounds, and they share electrons in order to complete the octet to get those 8 valence electrons. For ionic compounds, we typically have a metal and a nonmetal, and in order to get them to get their full octet or their noble gas electron configuration, the metal will lose electrons to become positive. The nonmetal will gain electrons to become negative, and those positive and negative charges attract, and that's what holds them together in the ionic compound. So, ionic compounds are pretty much all solids at room temperature, and they have all of these positive and negative ions that are combined in a way that minimizes the repulsions, minimizes the positives repelling positives, and maximizes the attractions between the opposite charges. So that is why they're typically solids at room temperature, is because they have all of these really strong attractive forces that keeps them together. They don't want to be pulled apart, and so melting them takes a lot of energy. In order to figure out the formula of an ionic compound, we just look at the charges and then we balance them out. In order to find the charges, if we don't have them memorized on the periodic table, we can always look at the electron configuration. So for example, here, calcium has this electron configuration, oxygen has this. In order for calcium to get a full octet, it could either lose 2 electrons or gain 6. It's going to be easiest for it to lose 2, so it's going to have a positive 2 charge. Oxygen, on the other hand, already has 6 valence electrons, so it's going to be easiest for it to just gain 2 rather than losing all 6 of those. So it's going to have a negative 2 charge. So we can use these electron configurations to see how many valence electrons our element already has and how many it would need to get to a full octet, whether it's to gain or lose. Remember that when we form an ionic compound, those charges must cancel out. So in this case, calcium would have a positive 2 charge, oxygen would have a negative 2 charge, and so they could combine in a 1-to-1 ratio because the charges would just cancel each other out. So there are charges that we can kind of predict on the periodic table. The first column is always positive 1. The second column is always positive 2. The third column is always positive 3. Remember the transition metals? We don't count those because they can be varying positive charges. They have to be positive because they're metals, but they may change from element to element and even within the same element. We typically ignore this column as well because they can vary, or they typically, a lot of them don't even form ionic compounds. The nitrogen family is always negative 3, oxygen's negative 2, and the halogens are negative 1. The noble gases, again, don't form ions because they've already achieved the full set of valence electrons. So in ionic bonding, we can think of it 2 different ways. We can think of it as the metal actually transferring its electrons to the nonmetal so that nonmetal now has the full octet. Or we can think of it as they've already gotten these charges and now they're just oppositely charged ions floating out in space that are attracted to each other. But either way you think of it, the main concept that's holding these ions together is this idea of the attraction between one atom that's positively charged and one atom that's negatively charged. So like I said, the ionic compounds are typically solids at room temperature because they have such a strong attraction between the positive and negative ions in their structure that it requires a lot of energy for them to melt. So the stronger that force of attraction is, the higher the melting point will be. So the greater the charge, the more significant that force will be. So larger charges will always be more significant than a difference in size between the ions. So, an ionic compound with charges that are like +3 and -2 will be more strongly attracted than an ionic compound with smaller ions. So if the charges are the same, that's when you'd want to look at the size of the ions. And this again goes back to Coulomb's law, right? Because Coulomb's law is force equals charge over distance. So the more charge there is, the more force there will be. And the less distance there is, the more force there will be. So the smaller the ions, the more force there will be. And so when we're talking about melting point, the melting point increases with increasing force. So the stronger the force between these ions, the higher the melting point of that ionic compound will be, because it's going to take more and more energy to pull those ions apart. Those charges are really strongly attracted to each other if you have large charges or a small distance. And so you're going to have just a higher melting point in order to get enough energy to pull them apart. If you have the charges that are the same, like if you're trying to compare two ionic compounds and everything has, it's +1 and -1 and +1 and -1 in the other compound, then you want to look at the size of the ions. If you have ions that are closer in size to each other, it's going to also have a higher melting point than an ionic solid that has very differently sized ions. So you want to consider that too, that comparison of sizes. So just a few properties of ionic solids. First of all, like we said, they have really strong bonds, which makes them have really high melting points. They're also hard, typically crystal structures, and they have a low volatility, which means they do not enter the gas phase very easily. So they don't evaporate very easily. They have a pretty brittle 3D structure. So even though their bonds are strong, these are not malleable or ductile. And that's due to the fact that the positive and negative charges are surrounding each other. And so if you try to pull on a ionic compound, those positive charges are going to get separated from the negative charges and bump into other positive charges. Suddenly you're going to have a bunch of repelling, and it's going to cause there to be a fracture in your material. They're also really typically, ionic compounds are typically very soluble in polar solvents. So water is a polar molecule, right? So they're typically pretty soluble in water or other things that are polar. And most of them conduct electricity if we dissolve them in water or melt them. So once those ions get broken apart, they can conduct electricity. As a solid, it will not conduct electricity. So ionic compounds are held together into these crystal structures by those oppositely charged particles attracting each other. So basically the way it works is the larger ions, the anions, because they gained electrons, so they're going to be bigger, they're packed into this regular repeating pattern that we call a crystal structure. And then the smaller cations, they're smaller because they lost electrons, those will fill in the gaps between the anions. So you can see in this diagram here, we've got our negative ions. The green ones are the chlorines. Those are on the corners of this crystal structure and on the faces. So you can see the different, just like kind of where the structure is. And then these positive ones are these sodiums. Those came in and filled in the space in between every chlorine atom. Sodium chloride's a 1-to-1 ratio, so it's easy to see here. We've got 1 chlorine for every sodium, and those sodiums are basically just filling the spaces between the chlorine ions. So in reality, they're not this far apart. This is just drawn this way so you can kind of see it. In reality, they're more closely packed, like in this picture on the right, where your sodiums are really snugly fit in there in between these larger chlorine atoms. All right, so on to metallic solids. Metals have some pretty unique properties. They conduct electricity and heat as solids, and they're one of the only things that is able to do that. They're also extremely malleable and ductile. Malleable means they can be pounded into sheets and they won't break. They can be bent, they won't break. Ductile means you can stretch them out into a wire, and again, they don't break. So these are properties that are pretty unique to metals. Metals are also in crystal structures, just like ionic compounds. So the metal atoms form that regular repeating pattern, just like the anions in an ionic compound. And they have this regular pattern that alternates between layers. We call this orderly pattern a unit cell. So these crystal structures for ionic compounds and metallic crystals all have a unit cell, which is basically what we can break down our structure down into one small piece that just repeats in all directions to create an overall solid. So here's a few different structures that metals form in their different crystals. And you don't really need to know any metals that form these structures, but just be familiar with the fact that there's these 3 different ones and kind of just what they look like. So a body-centered cubic has atoms at each corner of the cube and 1 in the center. Face-centered cubic also has atoms at each corner of the cube, but 1 on each face, nothing in the center. And hexagonal is, instead of forming squares, they form a hexagon shape, and there's hexagons in each layer. So these are some of the most common ways that crystals form for metallic solids. All right, so the way that bonding works for metals is a little bit weird. It's not covalent, and it's also not really ionic either. There's not enough electrons to fill the octets because the metals are all electron deficient. So instead, all of the metals will lose their valence electrons, basically. They delocalize them. They don't really lose them. But those valence electrons can move throughout the structure. And so the nuclei of each metal atom is attracted to all the valence electrons of all the atoms surrounding it, because those electrons are free to move. And this freedom of these electrons to move is part of what gives metals their unique properties. Like the fact that the electrons can move allows the metal to conduct electricity and heat more easily than, say, an ionic compound where those electrons are not free to move. So the strength of the bond increases with the number of electrons that are available to be delocalized in a metal. So we can look at that in terms of melting point. Basically, we can see how strong that bond is by comparing the melting points of different metals. The higher the melting point, the stronger the bond will be. So for example, sodium has only 1 valence electron that can be delocalized. its melting point is about 97 degrees Celsius. Iron, on the other hand, has 8 electrons that can be delocalized. And this is another kind of weird thing about metallic solids. While electrons in the d orbital don't typically count as valence, they can still be delocalized in a metallic solid. So they can still be part of that movement of electrons. So iron has 8 electrons that can do this. It has 2 in the highest s orbital and 6 in its highest d orbital. So it has a lot more electrons than sodium, which makes its bond strength much higher. Its melting point is 1,538 degrees Celsius. So you can see how that increase in electrons really increases the strength of the bond. So these movable electrons are often called an electron sea, or a sea of valence electrons. This is the model that we use to describe how metals are bonded. And basically, in this model, you have a regular repeating pattern of metal cations. We say they're cations because their electrons have kind of left them. And they're surrounded by this sea of valence electrons that can move. And the movement of those electrons is what allows for metals to be able to conduct heat and electricity. So you can see in this picture here, we've got all of our positive metal ions in their regular crystal structure, and then this electron cloud, or sea, that is floating around all of these positive ions, and they can move. They don't really belong to any particular atom, and that allows them to conduct heat and electricity. It also keeps these positive ions from touching each other because you've got these tiny electrons floating in between them at all times. So even if we try to stretch this or compress this to make a wire or a sheet or to bend this metal, those positive ions will always be insulated from each other by these electrons. And that's what allows the metals to be malleable and ductile, whereas ionic compounds will just shatter if you try and compress them. So metals can also form mixtures called alloys. An alloy is just a mixture of elements that has some metallic properties. So an alloy must contain at least one metal in the mixture. There's 2 types of alloys, substitutional and interstitial. In substitutional alloys, some of the metal atoms are replaced by other atoms that have a similar size. So some examples are brass, sterling silver, or pewter. And you can tell if atoms are a similar size if they're near each other on the periodic table. So for example, in brass, we have our regular pattern of copper atoms, but 1/3 of them is replaced by zinc. And so the copper and zinc are right next to each other on the periodic table. So this is a great example of a substitutional alloy because those atoms are nearly the same size. In an interstitial alloy, we have our regular metal crystal structure, but then the gaps between those metal atoms are filled with smaller atoms. Oftentimes, those smaller atoms are nonmetals because nonmetals typically have a smaller atomic radius than metals, just based on our periodic trends. So an example of this is steel. In steel, we have our regular iron crystal, but then some of the gaps between the iron atoms are filled with carbon atoms. When we do this, it really changes the properties of the metal that is making up the crystal. So iron by itself is soft, ductile, and malleable. But when we have steel, when we add those carbon atoms, it becomes harder, stronger, and less ductile. And so for some purposes, we want those properties to be different. And so we create these alloys to make a material that reflects the properties we need. And the amount of this smaller atom will affect the properties. So more carbon will make it more strong, less ductile. Less carbon will have the opposite effect. You can also add other elements to these alloys, so it doesn't have to just be two elements. So for example, chromium is often added to steel to make stainless steel because chromium is very rust resistant. Iron by itself rusts very easily, but chromium doesn't. So adding that chromium helps the metal alloy to lose that rusting property. So here's some diagrams of metals. In the top left, we have our pure metal, which would just be our regular crystal repeating pattern. Next to that, we have the substitutional alloy, so our regular repeating pattern where some of those atoms have been replaced by other atoms that are a similar size. Down in the bottom left, we have the interstitial alloy, so our pure metal structure remains the same, but now we have some of these much smaller atoms filling in the gaps. And then in this last box, we have one that, like this would be like stainless steel, where you have your regular pattern, which would be the iron atoms. And then there's the substitutional alloy, which would be the chromium, taking some of those places, mixed with an interstitial alloy, which would be the carbons filling in those gaps.